Okay, so this lecture is about neural networks, which is a very hot topic in the past several years. All of you have heard probably about deep learning and deep neural networks. So this would be an introduction to the basic concepts of neural networks and deep neural networks. And it wouldn't be, of course, anything advanced. There is a separate course on the basically deep learning and deep neural networks. I think there would be another one next semester offered, and there would be even a course on the more theoretical aspects of neural networks, the dynamics of learning of neural networks. That is also, I think, offered next semester. So if you like theory, that might be a good course. If you want to know about different architectures and algorithms, we have another course there. So here I just give you the basic ideas and concepts. And also I kind of get a sense that many of you already know about, have practiced with this deep learning, and now you're taking this introduction to machine learning course to know about other methods, more classical approaches. So neural networks. So let's go back to where we started a few lectures ago, and it was about this modular approach to learning, essentially, to design a machine learning algorithm. So we talked about, we said that, okay, we have this predictor or model that takes some input, does some processing on the input in order to predict the output, and then the output would be compared with the true value, the target t, and then we get a loss function that compares how good or bad the difference between these error, the prediction and the target is. And if you think about what we have done in the previous lectures, is basically we focused on mostly, but not always, focused on linear models. So we said that the output is generated by something like this, like x, inner product of x and w's. So the model is very simple, but then the difference between different lectures was more or less on the loss functions. So for example, we talked about hinge loss or exponential loss just now, or cross entropy loss for the logistic regression. I mean, there were some differences. For example, there was this activation function that was we use in logistic regression. But the models was mostly a linear model. Then we said that linear model is kind of limited, so let's make it stronger by you working in a feature space. So we would say that, okay, so let's take X, pass it through some feature mapping phi, and then have a linear model in that space. So by doing this, the model was not linear in inputs in X anymore, but still linear in W's. So feature mapping can make the linear models much more powerful, depending on whether we come up with a good feature map or not. But coming up with good feature map might be challenging. So one solution that we talked about was this kernel-based method, which is a way to partially address it. We say that instead of actually coming up with a feature map, we come up with with the inner product in the space of feature maps. And maybe it is easier to actually talk about the inner product and specify inner product than explicitly writing the feature map. So that was a solution for that partially addresses this problem. And you see that if you use kernel-based method, your classifier or your regressor would become much more powerful than a linear. And this was actually a solution that the machine learning community were using mostly in late 90s and most of 2000s. So kernel-based methods was the way to make more expressive models, yet having the simplicity of linear models. But then we have this another approach to deal with this problem and having more expressive and complex model, and that is called neural networks or artificial neural networks, to kind of differentiate between neural networks in brains. It's another way, general approach to represent more complex models. And of course, neural networks isn't something new. Some form of neural networks have been used in AI community in general, machine learning, since decades ago. So from the beginning of artificial intelligence, people used something like neural networks. But then it had its spring and winters. Maybe I talk about it in more detail later. So, but the idea maybe I just mentioned that in like 2000s, early 2000s, people figured out that artificial neural networks are very expressive, but training them is not easy, and they don't have. We can't say nice theoretical properties about them in the same way that we could say for other methods like kernel-based methods, and because training them is kind of some form of art, and is much more complex than, say, training of a support vector machine. Not many people were working on it. Of course, there were it wasn't like nobody was working on it. Say, people like Jeff Hinton were working on it actively all their career on neural networks, but it wasn't the majority of the community. But then later, people figured out ways to make training of neural network better, and also started to get results that were much better than kernel-based methods. Like even in 90s or early 2000s, neural networks were performing well, comparable with kernel-based methods. So they were not worse actually in performance, but training them was more complicated. But then when you get to stage that your performance is much better, people would be forgiving in having a bit more complicated training procedures. And I would say still it is, training neural network is not as easy as training support vector machine or linear model. There are a lot of arts there that you need to kind of know how to train them. But it is much easier than, say, 90s or early 2000s. Okay, so maybe I have another comment here is that, so you see that, okay, so we have these linear models. We make the linear models which does some processing on input, and the processing is a very simple processing of taking input, multiplying by some weights, and then producing the output. The linear model in feature space is basically doing the same thing, but before that does a little bit more processing. And that processing is computing a feature map. So neural networks, as you will see, is doing some other form of processing, which is more complex compared to what we have for linear models or linear model feature space. So one way I think we can think about essentially this prediction, any model, is that it's a computer program that processes the input in order to generate the output. Some programs are simpler, just compute the inner product of two things. Some are more complex. And neural networks are more on the more complex side. And different architectures of neural networks are essentially about what kind of program doing computation on the input in order to generate the output. And we get to the point that these programs can be very expressive and can generate very complex relation between input and output. Okay, so I think what is important, what we learn today or for this lecture, I don't think we can finish it, is mostly focusing on one type of neural network, which is called multilayer feedforward neural networks, or multilayer perceptron networks. And then the other one is, we also talk about how to train them through this algorithm called backpropagation. Maybe we talk about convolutional neural networks, or maybe not, depending on the time. But that's convolutional neural networks would be neural networks that are suitable for working with images. The concepts are very similar, but there are some kind of structural differences. Okay, so let's talk about neural networks. So the inspiration of neural network comes from the brain. So the human brain has a lot of neurons. Each neuron, I think it's about 10 to the power of 11 neurons. And each neuron is connected to many other neurons. So there is a communication between them. So I'm not a neuroscientist, so I'm not going to give you any detail of how a neuron works. But at a very, very high level, a neuron works something like this, that we have a cell body which has some inputs, dendrites, and it has some outputs, which axons. Each axon is connected to some other dendrites of other networks of other neurons. So there would be connections to other networks, other neurons. And then each of them basically receives the input from through its dendrites and then may produce some output in its axon. So how it works? The way it works is that if there is enough input or there is enough excitation in the dendrites, what happens is that then neuron becomes active and starts something that is called action potential. Action potential is essentially a kind of a change in voltage of on the neuron. So if this action potential propagates through the network, through the neuron, and goes through axon, and then it can excite other dendrites of other networks, other neurons. So this is very high level. This is the kind of high level inspiration of it. We try to, what is important in it is that each neuron has some inputs and has some outputs, and depending on whether the inputs are has enough, say, excitatory behavior, the neuron starts producing some output. So we try to model this thing with some simple mathematical formulation. The way that it works, or we formulate it, is saying that we have a neuron that takes some inputs, so x1, x2, x3, so three-dimensional inputs. Each of them, each of them goes through some weighting. So it's multiplied by some weights, and then some output y would be generated. The weightings in real neurons depends on the synapses, the connection between dendrites and axons, and how much the activation of one axon excites or inhibits the other dendrites. But we model it with just some weights at these connections, real valued weights. So we can write essentially the output of one single neuron as some linear combination of x's and w's, so w transpose x, perhaps plus with some bias term, which, as you saw before, we can kind of incorporate in one of the inputs, so we can consider all of it as one w transpose x. And then we have some activation function, which basically says that if this is the input to the unit, the neuron, then how much output it is generating. So activation function kind of mimics this behavior that for a real neuron, we have this thing called a threshold, which the neuron would only become active and produces some output in its axon if it passes some threshold. The total, say, input to its dendrites, if it passes through some threshold, it starts generating some action potential. So you see here that, for example, this is some stimulus to it, but this stimulus is below this threshold value, so nothing really happens. But if it goes higher than this threshold, the neuron becomes activated, generate this action potential that propagates through its axis. So this threshold function behaves, is mimicked by this activation function. And we will see that we have different type of activation function. So just as an example, maybe we can compare it with this model of each neuron with logistic activation function used in logistic regression. So logistic regression was essentially computing W transpose X plus B and passes it through activation function, which was a logistic activation function that looked like this. So this would be Z, for example, this would be Z, and this would be the Y, and Z would be equal to, say, phi transpose X plus B. So with this activation function, it is essentially like one unit of one logistic regression model. Okay, is there any question so far? Good. So now we define one simple mathematical model for one neuron, one unit, which was very simple. It was just linear combination of its inputs, weighting it, and then generating some output. Now we can connect many of them into some architecture and saying that the output of one should be input of another. One way to do it is that we can connect lots of them through some directed cyclic graph, a DAG, and then usually actually we put them in a very more structured form instead of a general DAG. We put them in the form of layers. So what does it mean? It means that, okay, so we have these inputs to the whole neural network. So this would define a neural network instead of just one neuron. So we have these inputs, X1 and X2. So this is essentially, it means that X belongs to R2 in this particular example. These units, these inputs goes to a few neurons, for example, neuron 1, neuron 2, neuron 3. These neurons, there are some weights, there's connections, you see that there are connections showing here. They do some computation based on some multiplying by some weights, and then they would have an output here. So there would be an output generated here, here, and here. So the output of these neurons now becomes input of the neurons of the next layer. So this goes, oops, this goes here and here, and maybe the other one, this one goes here, here, and here. So essentially they can be connected. Each of the outputs of each layer is connected to the inputs of each unit in the next layer. And then we can do this process again and again. So for example, we have another layer, second layer, and then here, then we connect it to generate the output of the neural network, which is called output layer. And that would be, again, say we have two outputs. So output Y, vector Y belongs to R2 again. In general, of course, the input and output are of two different dimensions. So what is important here to kind of the notations that we use is that, or what we call these things is that the input layer and output layer. So input layer is essentially the input of your model. It is X as what we had before. Y is the same as Y that we had before. And then we have each of these layers in between. They are called hidden layer. So here we have two hidden layers. So hidden layer 1 and hidden layer 2. This can be more than that. It can be 2, 3, 4, 100 or whatever that you want. So this architecture is called feedforward neural network. This because it is passing the information in one direction. It's in the forward direction. So we feed information or processing of process information forward. This is in contrast to recurrent neural networks, which can have cycles. So there wouldn't be a DAG architecture, but there can be cycles there. So we don't talk about it, but how it looks like would be something like this. That say what happens if the output of each of them goes back to itself. If we have such a process of architecture, that wouldn't be a cyclic anymore, and that would be a recurrent neural network. But we are not going to talk about it in this course. Okay, so let's go through the architecture a little bit, kind of look at it a bit more closely. So each hidden layer, I, connects ni minus 1 input units to ni output units. Ni minus 1, and I can be different numbers depending on the architecture. So for example, here we have ni minus 1, for example, if you call it I minus 1 is 3, and I here is 4. In the simplest case, all input units are connected to all output units. So this means that this one is connected to all the outputs of the next layer, and the same for all of them. This in general, this is not the case. We can have neural networks that only, for example, maybe I write a bit differently. So, for example, the input of this might only come from these two. An input of these may only come from these two, only a subset of all the outputs of the previous layer. But here, if it is connected, everyone is connected to everyone else, this is called fully connected layer, as the name suggests. And there are other types of layers, which we may talk about, like convolutional layer is another type of layer, which has very special structure that is different from fully connected. One thing to make sure not to confuse is that the input and output of each layer is different from input and output of the whole neural network. So when I talk about the input of a layer, for example, input of this layer, the input of this layer is the same as the input of the network, but the output of it is not the output of the network. Okay, so if you need to compute, say, m outputs from n inputs, and consider m to be, say, ni, n to the ni minus 1. So this might be a bit confusing. These n's are different from m and n that I'm using there. And also don't confuse it with n that we used before for the number of data points. So these are defined locally. So we can essentially do the computation in parallel using some matrix multiplication. So this means that we need to, we will be using m by n weight matrix. And the output of that layer is computed like this, that the y, which is, what is the dimension of y? Okay. Yes.
It doesn't have any change, just pass the input to the output of the input layer, and then it's going to the first hidden layer.
So this means basically like this. Okay, so the question is that what, like I said, if I want to summarize, what is the input of the first hidden layer, and is it the same as the input of neural network or not? So this basically means that here, so this basically means that if we call input, essentially input layer, so X is the input of the network, we call it X1 and X2. Maybe use a different color. This one just goes to, becomes the input of this first hidden layer. So the input of it essentially is multiplied by some weights and determines what goes inside each of the units of the first hidden layer.
Just our samples that go through the.
Yes, the input layer is just the inputs of the network.
Will there be weights added when you're adding to first?
Sorry, but say again, please.
So will there be weights added when you're adding to the first hidden layer, or is like we're just dividing it the input we're dividing it up for the first hidden layer?
So No, well, I guess we multiply it by weights, right? So that's true.
Even for input layer?
No, input layer is multiplied by weights to generate and go to activation function to generate the output of the first hidden layer.
Oh.
Like input layer considers just the input of the net.
Sure.
And then
My question essentially was, do we add weights after the input layer?
add weights.
Weight after input layer. So do we have an activation function after the input layer?
Oh no, sorry. Okay, so the question is, do we have activation function after the input layer? No.
Oh.
In general, no. Okay, so we get to this form that, okay, so the question was, I think I was asking is that, so what is the dimension of y? Okay, yes, so the dimension of y is equal to m. So this would be, well, general, like if the output dimension is m and input dimension is n, it would be m dimension. In this case, it would be 4, right? And the dimension of x is n dimensional, which would be 3 in this case. And then this matrix W would be essentially, can be written as a matrix which is m by n, that takes the inputs, does the computation, so it generates m-dimensional outputs, and then we add some bias term sometimes. Well, usually we add a bias term, which you saw before that we usually add to linear models, and then pass it through the activation function, which we will see a few examples of them soon, but you can think of it as the logistic activation function that we had seen before, like this one. So that can be an example of it. So there is a question.
Yeah, so does the activation function just apply it to each report? The one D function has to be the same each report.
Right. So the question is that if the activation function is applied coordinate-wise or element-wise in what models I'm talking about, yes, that would be the case. There would be other networks that activation function would be a function of a few outputs together. Like they take 5 outputs and just generate 1 output out of it. But here in this course, we just, at least in this lecture, I just talk about the element-wise application. Yes?
Would each of the y be a scalar? Like, would y1 be?
Yes. Yes. Each y would be, the question is that each y is scalar, and the answer is yes. So there is a question, are we changing our notation of bias for neural network? We used the embedded Y approach before, which allowed us to just use W. That's true. We said that we could put X's inside one, add 1 dimension to X's, and just not having a bias term. We could do the same thing here, but if you want to do it, essentially you can think of it as there should be always a L unit that generates Y1 as its output. So yeah, actually this is a good point. So the way we can do this is that, for example, if I want to avoid bias, I can assume that there is a 1 here, a unit that always generates Y1, and it is connected to all of them. So then this becomes 3 plus 1 equal to 4, and then I can write everything as phi of W x extended, maybe I use x prime, and now this would be 4 by 4 dimension, and there wouldn't be any need for extra bias there. So that would be also possible here, but I guess it is common to have a separate bias term here to kind of basically so that each X would not need any augmentation after each layer of computation. All right, so this multi-layer neural networks that is consisting of fully connected layers is called feedforward neural network, or multi-layer feedforward neural network, or sometimes multi-layer perceptron. So perceptron, but this is a kind of like a probably not a very proper name, because perceptron refers to some specific algorithm called the perceptron algorithm, which doesn't really have much to do with neural networks. You can think of it as a way of training single layer neural network that connects input to output, no hidden layer. It's a training algorithm for that. But I think what happened is that people confused the algorithm with the architecture and then said that, okay, so that was a one layer perceptron. Let's see what happens with two layer perceptron, multi-layer perceptron, and then that would be multi-layer perceptron. But then the way we train our neural networks these days is not like the perceptron algorithm. But you will see multi-layer perceptrons as the name for these feedforward neural networks. So that's why I'm using both names here. Okay, so let's see some activation function. So activation function essentially, maybe just a few slides back. So activation function was this thing that now we do some linear computation of the inputs of each unit. Then we need to do some processing of that linear processing after that linear processing, and that is done by an activation function. The simplest activation function is just basically saying whatever we get as the output of that linear computation, we just pass it along. So if we have Z here, and this is Y, the relation would be identity. So Y would be equal to Z. Another way to do it is, maybe I show it in different order. We do it something like hard threshold. We say that if Y is larger than, Z is larger than 0, then the value of Y would be positive 1. Otherwise, it would be 0. So the network, the unit is either, neuron is either outputting 0 or 1, and whether it is doing 0 or 1 depends on how large that computation of, say, W transpose X plus B would be. So this is the Z part of it. If it is large enough, then we output 1, otherwise 0. Does this remind you of anything?
0, 1 loss.
So that's true. Okay, so that's true, 0, 1 loss. But I'm thinking of what actual real neuron does in several slides ago in the talk in this part that I talk about the brain. So the thing is that it may remind you, apparently not, that it behaves somehow like a real neuron, that if its input, the stimulus is strong enough, so it passes the threshold, the neuron becomes active. And the level of activation, this action potential, would be independent of how much stimulus we have. But if it is the stimulus of a neuron is weaker than this threshold level, the neuron would not become activated, and the output of it would be essentially 0 and dies. So this threshold activation function is a way to mimic it. That if the input is strong enough, we generate output. If there is it's not strong enough, we don't generate anything. Of course, there's a lot of detail in a real neuron. There's this dynamics of it, which is ignored in our artificial neurons. So that's one. Let's look at another one, which is called rectified linear unit, or ReLU, which behaves like this, that it's 0 if the activation function, if the input is, that Z is smaller than 0, but it increases linearly after Z becomes positive. So this is something between this identity function and hard threshold. And if you compare it with loss functions, even though it looks like somehow like the hinge loss, but the motivation is not the same. And then there is a version of, there are other versions, like for example, soft ReLU, which looks like this. Or we have logistic function, activation function, which would essentially compute e to the power of minus Z, adds 1, and then the whole thing would, 1 would be divided by the whole thing. So the behavior of it would be that if Z is very positive, the output would be plus 1. Otherwise, if it's very negative, it would be 0. But the behavior is kind of smoothly changing between 0 to 1. So this can be seen as a softened version of this hard threshold. So this is kind of, if we make it soft. And then we have hyperbolic tangent, or tang H, which is very similar to logistic function, except that the output is either plus 1 or minus 1. And then in the region that Z is close to 0, the behavior is almost linear. But then when Z is very positive or very negative, it starts to saturate. Okay, so let's go back to feedforward neural network. Each layer, so now we know some activation function, and we basically know how each layer is working. So each layer, so we start from layer X input, it computes, the output of it would be, we multiply W1X, add some bias to it, and then pass it through some activation function in order to get H1. And now this H1 goes here, multiplied by another rate, some bias is added, going through another activation function, which may or may not be the same as the previous activation function. Here I'm using the same phi, but in general they can be different. We get H2, and then we do this process multiple times until we get that the last layer is computing, getting the input H of L minus 1, does some computation there, and generates Y. Or more compactly, we can write this whole process as a composition of several functions to its input. So we have a composition of function F1, F2, F3 to FL, and that determines the relation between input and output. This one? So this means a combination of two functions. So it's, I'm using this one. F and G of X, it would be F of G of X. So the thing here that is interesting is that this is a quite modular approach. Each layer can use different activation function, can have different inputs and outputs. They might, and if we can implement each of layers separately somehow, then we can easily combine these layers together to get the output of the neural network. And this would be important when we implement neural networks and makes much of the calculations much easier. Okay, so this is a kind of exercise. I think maybe we can try to, you think about this, maybe we can't do it now. Just write down the equations of a two-layer neural network, one hidden, one output, with two hidden units, and phi as an activation function, general activation function, and a linear one-dimensional output. So this is essentially x1 and x2, two-dimensional, like the whole x is two-dimensional, and then suppose there are two hidden layers, and there is, so suppose each of them are connected. And this function, activation function, there is one, sorry, it's phi, any phi, and the output layer is linear. So phi is linear, identity function. So just think about it. I mean, it's obvious, but I think it's good to write it down and see, to become a bit more comfortable. So so maybe talk about part of this slide. Well, how do we choose the last layer? It depends on usually the task. Like if the task is regression, where the output should be a real valued number, so the output layer is usually chosen to be just linear. So the activation function of the last layer would be linear. So y of f of L of input to that last layer would be W of weight of that layer, inner product with H, the output of the penultimate layer, plus some bias. So there is no nonlinearity here. But if the task is some binary classification, we do the same thing, but because it's binary classification, we want our prediction to be, for example, between 0 and 1, or -1 plus 1, depending on the whether it's 0, 1, or -1 plus 1 for the targets. So we do that. So that's why we have this activation function. So yeah, I think I should stop here. So based on what I told you, probably we don't have I guess we won't have a homework now, because the homework that I have in mind has a question on neural network. So it's good to know it. I don't want to remove that neural network part. So that's good. We don't have a meeting or lecture next week. I think that's a reading week, so there's no lecture supposed to be. And I will work on your project essentially now. I will post today or tomorrow some of the reading material, so you can now start reading things. Now you know about a good part of machine learning, so you can read something about, say, SVMs or boosting, or perhaps decision trees. So I introduced a few. I think that's all. Is there any good question?